Alright YouTube, today I've got a problem that I figured nobody would believe me if I didn't actually show you first. So here we've got a 50-gram golf ball hanging from a spring scale. And then there's 500 grams of water in a beaker sitting on a digital scale. Now, when I take the golf ball, which normally sinks, and set it in the beaker without touching the bottom, now the spring scale reading decreases. It goes down to around 5 grams. That's not a huge surprise because, well, the golf ball is trying to float in the water. But the piece that people have trouble wrapping their heads around is the idea that the digital scale went up. And so what we're going to do today is go through and solve for exactly what the reading on this spring scale should be, as well as the reading on the digital scale. So let's get this down on paper to work out exactly what's going on in this problem. So we've got a golf ball which is tied by a string to a spring scale. And that golf ball is submerged entirely in a beaker of water, and that beaker is sitting on a digital scale. And we're going to go through and solve for the reading on the spring scale as well as the reading on the scale down here. Now in this problem, I'm not really concerned with the mass of this beaker and the mass of the water itself. So ultimately what we're going to do is we're going to act as though we had zeroed out this scale after putting the beaker and water on it. So ultimately the scale down here is simply going to read the weight or mass which it's supporting because of this golf ball sitting in the water. Alright, so the first thing we're going to do to solve for both of the readings on the spring scales is take a look at all the forces which are acting on this golf ball. First and foremost, there's the force by gravity acting on this golf ball down. Then there's going to be the string acting upward on this golf ball. And last, we've got the buoyant force. See, this golf ball is submerged in this water, and therefore there's going to be a buoyant force acting upward on the golf ball. Now, this golf ball isn't moving vertically. What that means is, vertically, the sum of all forces adds up to 0. So inserting these three forces into this equation for our net force, we're going to have the force by the spring scale acting upward, plus the buoyant force acting upward, minus gravity, which is acting downward. Now, some people might be tempted to say that this digital scale down here is also holding up the golf ball, but realize they're not actually touching one another. This golf ball isn't sitting on the bottom of the beaker. Now realize it's this force by the spring scale up here which we're in fact trying to solve for. So we're going to need to work out these other two values. Now our buoyant force acting on this golf ball is going to be given by the density of the fluid, in this case water, multiplied by G, multiplied by the volume of fluid displaced. Now realize in this case the volume of fluid displaced is in fact going to be the volume of the golf ball. And that's because the entire golf ball is under the water. So subbing in our values here, the density of the fluid, in this case water, is 1,000 kilograms per cubic meter. G is 9.8, and the volume of the golf ball, because it's a sphere, is going to be 4/3 pi times the radius, which we've been given in meters cubed. And the buoyant force acting upward on the golf ball is going to be 0.437 newtons, which equates to about 44.6 grams. Next, there's the force by gravity on this golf ball. Now, the force by gravity is simply given by the mass of the golf ball multiplied by G. So we've got a 50-gram golf ball. It's 0.05 kilograms multiplied by 9.8. And we find the force by gravity is 0.490 newtons, which of course converts to 50 grams, the mass of the golf ball. So now that we have our terms for buoyant force and the force by gravity, we can go back up here to our original equation in the y-axis and solve for the force by the spring scale. And we find the force by the spring scale is 0.053 newtons. Now typically a spring scale would also show forces in grams, even though grams aren't a force, and that would convert into 5.4 grams. So what we see here is the ball is partially supported by the buoyant force and partially supported by the spring scale. So the spring isn't actually reading the total weight of the ball. So we've solved for the force and reading up here on the spring scale, but this hasn't addressed this issue of why this scale down here would read any value other than the weight of this beaker and water. So to get at that issue, what I want to back up to is Newton's third law. You see, Newton's third law says for every action force, there's an equal and opposite reaction force. And ultimately what's happening here is it's the water which is pushing upward on this ball. And therefore, there's going to be an equal and opposite force by the ball downward on the water. Ultimately, what that means is the water is being pushed down by the ball, which means this scale is going to have to push up a little bit harder in order to support the water. See, fundamentally, this really isn't any different than if rather than having a beaker of water on the scale, we stuck a textbook on the scale. Then if we added a second book on top of the first, we would see the reading of the scale go up. The key being that just like this bottom book is holding up the top book, the water is holding up the ball. So ultimately what that means is when we place this golf ball in the water, the reading on this scale is going to go up by a magnitude which is equal to the buoyant force. So I hope this explanation has been helpful, and on that note, that's all for now.